Okay, in this chapter I wanted to introduce a method to get more realistic description of alloys. And basically it means that we need a more complete or more complicated interaction model for the atoms in the alloy. And just to motivate, perhaps I make some notes to let you see what we do. So until now, we assume that the energy, the potential energy of a configuration is just given by the number of AA pairs and so on. So that's the very simplest model, and I use it quite a lot. So first step to enhance this, I already showed you can do it on different neighbor shells. So for first neighbors, second neighbors, and if you like, even further distant neighbors. But this does not change too much, so it's not a very, not very fruitful extension. And a more systematic way to do it is a so-called cluster expansion. CE. I do a similar approach as like here, so I write it a bit different, but basically it's the same. So you have a constant term plus, I would say an irrelevant term here. Guru used this notation before. The sigma I is plus or minus 1, or just the occupation variable. Position I in A, and plus 1 if we have an B at this position. So this is kind of self-interaction which we can completely neglect. Then the second one is in principle the term I had here. Now I have to sum over all the pairs. And not to double count, I can write it I smaller j. Now we have a j, I, j. I put 2 here, sigma I, sigma j. So that's the summation over all pairs. That's the term we used here. This would correspond to this chemical potential difference if you keep it here. And now we can continue this series. I can also count over triples. A, I, J, K. So that's a triple interaction. And this you can continue. Do it for quadruples and so on. And of course, these Jij or Ji, Jij, Jijk, and so on. They will depend on the type of atoms they connect. That's not all. I mean, for a pair, it's a pair, yeah. I mean, perhaps with a certain distance. But for a triplet, this can be a linear triplet, or it could be a triangle, or something else. And even more for a quadruplet. So there's more than just linear arrangements. Of the atoms in the cluster. So for a triple, for example, triplet, we could have something like this. This could be A, B, A, or A, B, or whatever, yeah. So you have different occupations of this cluster, and then besides this linear cluster, you can have triangular cluster, or something like this, and so on. So you see there is quite a number of different clusters possible. Yeah? And question is how to handle such a huge amount. Here you see it a bit nicer plotted here. So here you see some different triplets on an FCC lattice, which are possible here. So that's a first neighbor triplet. This is a triplet with two first neighbor, one second neighbor. Here that's a third neighbor and two first neighbor, and so on. Yeah, so these are all triplets. Here is one quadruplet. Oops. But of course there are even more quadruplets possible. Yeah. And a student of mine, he went through all this, and he used an approximation where he used 11 different pairs, 7 triples, and 1 quadruple. So that's a quadruple. I'm not sure. Yeah, these are all the triplets. The pairs, they just have different distances. How do we obtain then energies for these arrangements? Basically, this is a question. Yeah? So here's again what I just wrote. This is for the pair interaction and the single interaction. And now that's a continuation that you have quadruples, triples, and so on. Yeah? And always remember this can also have different occupations. And this can be done with an automatic toolkit, AT or ATAT. Perhaps I should write it down here. These interaction parameters. This is what is it? Alloy theoretical. I think that's what it stands for. Automated. What's this acronym? But in principle, this idea is not very old, not very new, sorry. I think it was in the 70s, 80s, where something related was developed. This was called cluster variation method. So they again considered different types of clusters, and then, like I did in this mean field description for the ordering phenomena, you can write down equations for the free energy as a function of these different clusters, and then minimize for all these cluster types. Of course, you have a number of constraints. A triple also contains certain number of pairs and so on. It's a quite complicated thing. And here's something else I remembered when I prepared this talk, what I tried to understand a long time ago. An even simpler approach, if you have just two pair interactions, epsilon 1 and epsilon 2. So first and second neighbor. Then you can draw a map of the ground states which are possible. So if epsilon 1 is positive, epsilon 2 is positive, then you expect to have precipitates. If epsilon 1 is negative and epsilon 2 is positive, you get ordering. This was the case I showed. If you have 25%, so there is in principle the concentration, a further variable here. At 50%, you expect the L10 structure. And here, when both are negative, this is a kind of competing interaction. Yeah, you want to have ordering on the first neighbor shell and on the second neighbor shell. So there's a whole bunch of different ordered structures. They are denoted here. This strange notation, and so on. Then you can consider here epsilon 1 positive and epsilon 2 negative. Then you get another type of ordered structure. This is the number of neighbors on first, second, third, fourth shell, I think, and that's at 50%. And here at least, here's at last, here's no structure expected. So this is the ground states. To obtain such a map, and this was done for interaction up to fourth neighbor, if I remember correct. This is called Kanamori inequalities. It's a tricky way to derive, but not if you look it up. I think you even found a Wikipedia article on that, but you don't find lots of literature on these Kanamori inequalities. So basically, now we are doing something similar, but since we have a computer, it's much easier. So what is done? You take all kinds of possible structures on an FCC lattice, for example. If you are interested in FCC lattice, it's still in rigid lattice model. Yeah? So you take an FCC lattice, you put A and B atoms on this structure to create ordered structures. Here's some examples. L10 structure, that's this layered structure. Truly it's a tetragonal structure. Or here's the L12 structure. They both appear in the copper-gold system. That's why I marked it here with gold and copper. Or you have the DO22 structure, the L11 structure, and so on. So there are 100% as easy as it perhaps looks like. I mean, in these DFT codes, there is still a number. I mean, they are called ab initio, so requiring no input except the atomic number or so. There is a bit more, so there are cutoffs and other things you have to take into account. Furthermore, I think up in it is a pseudo-potential code. I don't know whether you're familiar with DFT. There are full potential and pseudo-potential codes. Full potential means, in principle, I mean, you have so many electrons in an atom. So for example, for gold, I don't know what's the atomic number of gold, 50, 60 something. Any chemists among us? They should know. So you have a huge number of electrons, and in these ground state calculations in DFT, in principle, you have to take into account all electrons. Yeah? So it's the numerical effort is exploding when the elements get heavier. The pseudo-potential codes, they treat only the outer electrons as relevant, and then they have that's why it is called pseudo-potential, the core of the nucleus plus the inner electrons, which are treated as one common unity. It's much faster, but it's not as precise, and this up in it is a pseudo-potential code, but it also means if you use these inner electrons to shield the nucleus, that the potential between the outer electrons and this core is not a priori clear. Yeah? I mean, if you have just a real nucleus, it's a Coulomb potential. But if as soon as you have such a shielding, it's getting more complicated. So these pseudo-potentials, they're an art of their own. So it's not that simple as it sounds, perhaps. Okay. So this I already showed. And here now you find the values which finally turned out after this optimization procedure. Here for the zero energy, which is just shifting it up and down, a certain value here for the single atom energy. And then you have the pair energies here. And here you see these are the connecting neighbor vectors here. Yeah? So that's a first neighbor interaction. Has this value here. This was done for aluminum copper, a system which forms these nice Gini-Preston zones in which we are interested. Then you have an interaction to second neighbors, to third neighbors, fourth neighbor, and so on. I think up to 10th neighbor or 11th neighbor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Out to the 11th neighbor. That's quite a bit. Yeah? And you, as an optimum, he found all these values here. Then you have a set of triples. No, oops, sorry. And yeah, sorry, here are the triples. This, I guess, is probably a first neighbor triplet. There are 24 different ones and so on. Yeah. So again, you have a huge number of, this is the multiplicity of such triplets. And then finally, there was one quadruplet taken into account. How do you control now that you did enough, that you took enough of these interactions into account? That's shown on the next slide here. This somehow resembles these ground state obtained by the Kanamori inequalities. So what is done here is that you plot these values obtained from DFT, these are the crosses, as a function of the copper content, if you have aluminum copper. So these are all the values for all these intermetallic phases which were studied here. And here you have different points, blue circles, yellow circles, red circles, which all correspond to one particular cluster expansion. So a set of these values, J1, J2, and so on. Yeah? And in particular for the red ones, you see that they nicely fit these ab initio energies. So that's one step. Here's one lying out. It's strange. But most of these values correspond nicely. And also here in the interior, you find good correspondence. Okay? Now what is this straight line or this set of straight lines? That's a convex hull. What does it mean? We are at 0 Kelvin, we don't consider temperature until here. This means that this line just connects the ground states which are possible. So here, this is not the L12 structure. I come to this structure, what it is. It's marked here aluminum 3 copper on 100. And there are other structures. Here is one at 60 something, the by far lowest energy. And there are not many ground states here. And that's again an indication whether you did it correctly, whether you find the correct ground states at a given composition. I think this red circle here for this state is a bit away from the real. So here, if you put just these ground states according to the red points, you would have something different. But okay, it's still nice enough. So that's now the procedure to obtain our interaction parameters. And now you can start running a Monte Carlo or something else with this set of parameters. Except now the energy calculation is a bit more complicated as it was for pair interactions. And one drawback is that an implementation of, an implementation of vacancy algorithm is not too complicated. You would have to do the same, so to say, for a ternary system. So for a system containing A, B, and vacancy, this is feasible. But this residence time algorithm, I think, is hardly possible because you just have this huge number of clusters, so you cannot calculate all the possible transitions from one state to another state. So you're probably stuck, or at least we did not find a way to use the residence time algorithm here for these complicated clusters. And here is, I'm far too fast, nearly finished. Here's an application, what his name is Tobias Stegmüller. I already used some other slides from him. What he did with this cluster expansion. So first here you see a real experimental image of such an aluminum copper alloy with 1.2 atomic percent of copper. And I think I mentioned already that in these aluminum copper alloys you have this natural aging. So you form the precipitates at room temperature, despite the fact that it should not be possible if you just consider diffusion length or so, because you have a pretty high number of excess vacancies. And I don't know whether you can see it from the back. These are all single atomic rows, so that's a transmission electron microscopy image. So these are all copper atoms. These are Guigné-Preston zones, single atomic layers of copper on 100 planes. Since it's cubic, you have here another one, and that's another point here. But this was another student. He also evaluated the brightness. There are brighter spots and darker spots. And this is scanning transmission electron microscopy with so-called Z contrast. So the contrast nearly exclusively depends on the atomic number in this column you shine the electrons on. And he evaluated the brightness of each spot here. Each spot corresponds to one atomic row. And from this, using these Guinea-Preston zones as a calibration, he was able to determine how many copper atoms you have in one column. And then he added up, and I don't know whether this was by chance, he arrived at the true composition of this alloy. Very close. Okay, but that's not what I wanted to show. Okay, so these are these Guinea-Preston zones. I showed another example where I tried to motivate why they have this nice plate shape. But here I wanted to show something else. Here, for example, you see two of these Guinea-Preston zones with a spacing of 3 aluminum layers in between. So that's an aluminum 3 copper phase. And that's indeed the phase which is one of these minimum points here. It's a GP2 or theta double prime phase in this aluminum copper system. Yeah, and applying these potentials, he started with as we do in Monte Carlo, he started with a homogeneous alloy and then let it age for some time. And indeed, it formed nice Guinea-Preston zones. If you just consider nearest neighbor interaction, you would never get platelets. And he was also able, I think it's visible on the next slide here, he was also able, here is after a long time, so that's the initial point here, solid solution, here in a simulation with 1 atomic percent, after a very long time, so there's finally only one Guinea-Preston zone here, very nice platelet. It's slightly higher concentration. You get this double layer with 3 aluminum layers in between. So that's one thing he obtained from these cluster expansion data. And then what he also did, I showed the method to derive phase diagrams in Monte Carlo. He did something similar. He derived a phase diagram. Here, these are the red points, the Monte Carlo phase diagram, and the crosses. Because this is a metastable phase, it's not so easy to determine a phase diagram experimentally here. Yeah? So that's why these data points have a very high scatter. But you see that, grosso modo, this red curve well describes the experimental phase diagram. As I said, this metastable phase diagram. Of course, you find rather reliable equilibrium phase diagrams for such systems, but to find metastable phase diagram is quite difficult, I would say.
After
Yeah.
that time, for MC you have to write your own code.
Yes, that's what he did. Yeah. I think it was not an optimum code. I think he used Python. But part of the calculation, I think, was done in C, but it's not a very fast code. So I also proposed him to rewrite it in a compiled language. These calculations took quite some time. Here you see another snapshot. Here is the start, or for early times. And for somewhat longer times, you see the formation of many of these GP zones on 100. So you have 3 variants on 100, 010, and 001. So you find all of them. Here you find with an orientation here, here, and these ones are the other ones.
And how is the time evaluation? That is just the MC steps.
Yeah, we had a discussion on the time scaling here. How was it done? I have to check again. I forgot. Because he also did something else. I mean, if somebody is interested, I can also say something about the other algorithm he applied there. It's a bit confusing. The other method is called cluster evolution algorithm. It has nothing to do with the cluster expansion here. That means that you write down an evolution equation for the number of clusters of a certain size. So it's a bit the Specker-Döring model. Yeah? And for this, you need input data. This input data he obtained also from Monte Carlo, so the interfacial energy and so on. And there was a pretty high discrepancy between the time scales in the cluster evolution and the Monte Carlo, and I think also in the experimental data. But by a simple rescaling, one was able to bring them on one axis. So if there is interest, I can also say in one of the next lectures something about this cluster evolution algorithm.
And the visualization is using some Python.
I'm not sure whether he used Ovito. Might be that he used Ovito. So I should look it up in the thesis or ask him. So this was at 1% copper here, which is, it's a typical, I think in technical alloys, I mean in technical alloys they always count in weight percent, not in atomic percent. So I think this corresponds to 3 or 4% in weight percent. So that's at 0.5% here. You see that it takes much longer, or not much longer, a bit longer, to reach this precipitation state here. And I think it's also for 2%. And as I already showed, at 2%, you see the formation of these GP2 precipitates here, these double layers of copper atoms here. So I can look up he also did it for different temperatures. Here you see a table of, here's at one temperature for different times. Here you see at one time for different temperatures, raising temperature. So, and of course, at elevated temperature, things proceed faster. It's not very astonishing. I think this was all I wanted to show about this ATAT algorithm. I could show a bit more pictures, but I can also make another lecture just from the thesis. Is it this one? No, it's not this one. Oh, here it is. Here's this question of time scale. So here you see the Monte Carlo. Here you see this cluster evolution algorithm. And then if you
translate, they fall on the same curve.
Pardon?
If you translate, they fall on the same
right,
curve.
yeah, it's just one constant scaling factor in time here, which is required. So this is I think this is what he obtained, and this is a rescale, the orange one. I think these are experimental results here, and that's for this cluster dynamics here. This is dashed line. Oh no, I was wrong. So the cluster dynamics in the Monte Carlo, they fit well. They just do not fit to the experimental data. This was the point. And you also determine size distributions. Here. this one. Here he tried to fit this transmeal kinetics. Here's what I was searching for. So that's the average cluster size here from Monte Carlo and from this cluster dynamics. This, I think, is the precipitated volume fraction. That's the cluster density, which first goes up if you form nuclei, and then it goes down again. And these graphs are these cumulated cluster size distributions. Yeah? This one here. And you see that Monte Carlo also has a problem with very small, with very large clusters, because then the statistics gets very poor. Just checking whether this picture I showed. So you can take all information, like in any Monte Carlo simulation, out from such simulations. The only drawback is that since the interaction model is much more complicated, as we had before, the system size and the time you can cover is more limited as it is in standard Monte Carlo. That's why he also tried this cluster evolution or cluster, what is it called, cluster distribution kinetics or so. But as I said, if there is interest, I could also say something in another talk about this cluster evolution algorithm. Okay, so this is this ATAT method, ATAT toolkit. It's really available, as I said, and you can download and install it and try to run it. And I'm not an expert on this, but my student, he is still available. He can explain you how to use it and which parameters are important and so on. Okay.
There are many different ways of analyzing simulation results, and we have already seen some, and we will see some more. For example, if you are doing MD simulations, you can get lots of structural information, you can identify interfaces, and you can look at their fluctuations and so on. One of the important algorithms that is used in Monte Carlo a lot is the Horschen-Koppelmann algorithm, and the algorithm is used to identify the number of clusters as well as their sizes. Okay. The algorithm itself is very nice and fairly easy to understand, and this was published in 1976, and the algorithm that I am going to show, there is an implementation by somebody, computer scientists. So, that is an algorithm that is available online, which I have taken, I will show. But there is also a Wikipedia page which also explains what the algorithm is. But I think if you do it once, so I am going to do it on a very small system to explain what the algorithm is, then it is fairly easy to understand what it is doing, and you can think about extending it for other cases and so on. So, we consider an AB alloy, and let us say it is phase separated, and we want to identify all A clusters and count them, right. How to do is the question, and I will use the same example that is there in this hk.c code. Okay. So, this is an 8 by 8 array. That is the first line. That is the second line. something like that was there. Let us say that this is my lattice, so it is a 8 by 8 lattice, and 0 and 1 represent A and B, let us say, right. We want to count the number of clusters, and the algorithm goes like this. You can start from whichever point. I think the algorithm here starts from bottom and then goes. So, he is always looking to the top and to the left. I am going to start here. So, you can also implement with periodic boundary condition, but that is not what we are going to start with. So, let us say this is all my lattices and I want to find out how many clusters are there, and let us say I am interested in A clusters, that is clusters of 1. Okay. So, that is why, Sushil, if you have pure material, it will show one single cluster, because everything is 1, it will show that it is one cluster. Okay. So, you need A, B or clusters to know. Similarly, if you have a matrix and if you look for matrix, it will still show as one cluster, because everywhere it is connected and the algorithm will mark it as one. Need to look at the precipitates to really know the clusters. So, let us say that I start from here, and first time you see this number, and so you identify whether it is A or not. It is A, and so this is a cluster. Let us say that I label this as 1. Let me do this here. So, I label this as 1. Now, I go to the next site and I look at to the bottom and to the right. So, there is 1. So, cluster 1 is here also, and I keep doing this. I look to the bottom, to the right, and I see that every time there is 1. So, all of this forms one cluster. Now, this is site which is having B atoms, so it is not part of A cluster. This is not part of A cluster, this is not part of A cluster, and so on. So, and there is 1 here, right, and this is also part of this cluster because it has continuity with this. So, you can see that this is form a part of this cluster, and while doing this we also keep track of how many points are there as part of this cluster, right. So, up to this it would have been 8, and at this point it would have become 9. So, you have a cluster which has 9 lattice points up to this. Now, we go here and we see that to the right and to the top you see there is nothing. So, I will mark this as cluster 2. So, this atom belongs to cluster 2, because I see to the top and to the right there is no other A atom. So, and go here, these are all B atoms, does not matter. I look at this, look at to the top and to the right, you do not see, right. So, I will leave out. So, here I will mark it as cluster number 3. Now, cluster number 2 has 1, cluster number 3 has 1, and then this site is free and this is 1. So, this is 10, right. I am having a counter which is telling how many points are there in that cluster, and every new cluster gets a new number. Now, this is 2. So, this is also 2, and there are 2.00. This must be cluster 4. There is 0. Maybe I should put the 0 so that you can clearly see what is happening. This is 3, because third cluster now has 2 points, second cluster has 2 points, fourth cluster has 1 point. And this is 0, and this is cluster 1 which has 11 points. Now, here again it is 2 and 0, 0, this is cluster 4, this is 0, this is cluster 3. Now 4 has 2 points, 3 has 3 points, 2 has 3 points, 3 has 3 points, 0, 1, this has 12, right. So we have got 1, 2, 3, 4, 5. Let us go to the 6th line. Now this is 2, so it should be 4, 0, 0, this is 4, 3 points. Now you see this point, it has also 4, okay. So 4 points. Now you see this point, this is 3, 4th point, but it has this neighbor. So there are these 4 points also should be part of 3. So when you reach a point like this, you take all of them and change their label to 3 and add to this 4 these points plus 4, right. Now this cluster has grown by 4 because it just took over all this, and there is a 0 and this 1 is 13. And because this has taken 4 for this 4, so a cluster 4 for which the number, what is the n of M4, and I am going to make it minus 4, because I have taken this 4 and I have added 2 here. So 4 has a negative number, okay. Now this, now you go here, 1, 2, 3, 4, 5, 6, 7th line, right. At 2, this is 5, this is also 2, 6, 2, 7, 2, this is 8, right, which is with 4, which is same as 3 now. So 3 has 8, plus 8 I will add, I will make it 16. So for 3, now I will make n of M3 to be minus 8, 2, and then 0, 0, 0, 1, this is 14. Now we go here, 0, 0, 0, this is all 2, 2, 2, 2, 0, 1. So this is 15 and 16, 17, 18, 19. So you can see that there are only 2 clusters, this is one cluster and this is the other cluster. That is why if you run the code, output Hoshin-Koppelman reports 2 clusters, and you can see the clusters, they are all numbered 1 on the top and the right margin, and the rest of them are all numbered 2. How did they get 2? This is how they got 2. This is basically the algorithm, okay. So that is what is explained here. So you want to find out A clusters, you go to site I and you see if it is occupied by A atoms. If no, you go to the next site. If yes, then you look at its neighbors. Even though it says search all neighbor sites I, here you do not have to search all neighbor sites I. Depending on which direction you are going, we only looked at what is there to the top and to the right, right. So depending on how you go, and you will see that the algorithm implemented has up and left is what it looks for. So you search all neighbors I, if A neighbors are found, you have to classify. If there are no A neighbors found, then that will get its own index. It is an A atom, but you do not have any A neighbors for that. So it will get its own index. Okay. And while indexing it as cluster 1, 2, 3, etc., you will also start a counter which says how many lattice points have this, so that you know you have an idea about the size of the cluster. That is all we did. We went, okay, this we kept adding and when we found a new one we said okay, this is cluster 2 and started adding its numbers. And when they meet, then we have to take the smallest cluster number as the part of the cluster, because I can also say that it is not all 4, it is all 3, it is the same cluster. So, how you label does not matter, but just to be consistent, to make sure that clusters 1, 2, 3 etc. go and there is no missing cluster numbers because you merged it with something else. So, we take in whichever case is the smallest cluster number to be the, for example, when we came to this point there was 4, there was 3 and we just decided to use 2 because that is the smallest number as far as we are concerned. At this point we decided to use 3 because that was the smallest number. Then later you see that 3 itself is not the smallest number, 2 is the smallest number, so it becomes 2. Okay. So, apply routine classify. So, assign site I a new cluster label k plus dk and dk was 1 in our case. What is this routine classify? This is what it does. So, if it has a neighbor with site A, it is part of the same cluster. There is more than one atom, then smallest of the cluster label is the appropriate cluster label for the current site. If the neighboring cells have differing numbers, they are all the same cluster and use the smallest of the labels to identify this cluster. So, that is basically what the routine classify does. Now, this is given in the algorithms language as a union and find algorithm. You take, you club them and you find the smallest label for them. They are all equivalent classes in their terminology, like 3 and 4 and 2, they are all equivalent classes. You union them, you put them together and you find what is the least of the labels that you have to give. And this is a simple implementation of 2D with union and find. This is, if you go to the Wikipedia page, it does, and Wikipedia page does this also, except that instead of 0, 1, they have squares which are white and black and they follow the same algorithm. Okay, I go to a black site, how many black clusters are there, I look around and then I start labeling them 1, 2, 3 etc. and then I start putting them, making them unions, putting them together and changing the labels. The advantage, as you found, is that I rostered only once, okay, and just by one rostering I identified that there are only 2 clusters. The most important thing is the bookkeeping that you have to do, right. If I add up, so I said 19 here and 15 here, so that is what, 34, right. So, remaining should be zeros, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Did it come to 64? 30? Do you see 30? Yes. 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I seem to have 31.
23 plus 7.
Ah, okay, this is 1, sorry, yeah. Okay, so that is the bookkeeping. You count the sites and at the end, if you add all of them up, you should get the right number. So, that is all you need to do, and this is a simple implementation. I will show you, these functions are also very trivial. I mean, these are just simple comparisons and things like that. Of course, you can extend it to periodic boundary conditions, right. Here we said that this is, if I had used periodic boundary condition, there would have been only one cluster, because this is the same as that, then I would have labeled everything as 1, right. With respect to periodic boundary condition, there is only one cluster here, because this one and this 2 would have already been identified as the same, and that would have got the number 1, and you would have said that there is 1. Okay. And these algorithms are used for knowing what is known as percolation. Percolation meaning, if I start on 2, for example, is there a way for me to reach this end just by hopping through the 2's? Okay. Now, is this matrix percolating? It is not, right. I can't start on zeros and then come out on a 0 at the other end, nor can I do it from this side.
So cluster 1 is percolating. You can go from
Cluster 1 is percolating from here to here. Okay. Yeah, this end and that end, that is percolating, but zeros are not percolating. And why is this percolation is important? That most of the times, I mean, when I learnt about percolation, I learnt because you can have, for example, a composite, and if one of them is a conducting phase, and if it is percolating, then you will have the conductivity through that percolating phase. It is possible, right. If the good conductor is percolating, you will get good conductivity. The other one is what they call as open pore structure. If the pores are percolating, then you can enter one end and you can come out at the other end. You can pass a fluid through, for example, or gas through, for example. But one of the interesting examples that I had learnt about from an article by Robert Kahn in Nature, he had this, he used to write a column called News and Views, and one of them talked about a problem which is related to the mining industry. You mine gold, and there are always some small amounts of silver impurity in it, and it is very difficult to get rid of them. That has got something to do with the thermodynamics that Ferdi discussed the other day, because you take pure gold, you add one silver atom, there is so many states that is available for it. So, the entropy is so high configurationally that it is very difficult to remove that one single silver atom, because the entropy rate of increase of entropy as you reach pure A or pure B is infinity, because of which adding one atom of A to B or one atom of B to A is very, very favorable. So, if you want to remove impurities, the way to remove impurities in this gold is to actually add more silver, so that silver reaches a stage where it starts percolating, and then there is a way to leach it out using acid. So, that way you can get much more pure gold. That is, you want to purify gold, the first step for purification is actually adding the impurity itself. You add it so much that it will percolate, and then you can remove it. So, he talks about it. It is a nice article called the percolation frustrated. Okay, this afternoon we were looking at it. So, take a look at it, and this kind of process of purifying was also known. I do not know if you know about this Mayan gold or Tumbaga gold, they call it. Do you know that Spanish guys went to South America and got lots of gold, but they are pure gold only on the surface, micron or so. That is because it is again the other atom is leached out on the surface, so it is pure gold, but inside it is basically an alloy. Okay, it is not, rest of it is not gold. It has, I think in this case we found that it was copper and gold. Okay. So, this I mean, so there are many practical problems where percolation is important, and this is a strange example where percolation is important. And you can see this article, Kahn also talks about divacancy movement and how that helps in setting up a percolation in some zinc system, and how some impurities, if you put, they bind these divacancies, do not allow them to move around, and so percolation will not happen, and so on. So, that is why the article is percolation frustrated. So, if you have some impurities, they will not allow this divacancy movement and will stop percolation and so on. Any case, so percolation is many times very important for us. We also did something, you had something? No. So, we also did something, we generally tend to think that larger volume fraction phase should be the matrix phase. Some cases it can be inverted. Classic example is nickel based superalloy. You will have a channel of gamma which is very thin and large volume fraction of gamma prime, more than 50%, but still gamma prime will remain as a precipitate. That is, it will be islands. You can't start on one gamma prime and hope to reach the other end, whereas through gamma channels you can do this. So, that happens, and this is known as phase inversion. So, some microstructures if you have, whether it is percolating or not will tell which is the matrix phase. Typically the percolating phase is the matrix phase. Typically also the larger volume fraction is the matrix phase, but in some cases it is not. In nickel based superalloys it is because of the elastic moduli difference, or speculated to be because of the elastic moduli difference, but there could be other reasons. I mean, I think in some polymers, depending on flow properties, the more flowing one becomes the matrix and the less flowing one or more viscous one becomes the island, what we would call as precipitate. Anyway, there is also an implementation of Hoshen-Koppelman, which was written by one of our master students in Python recently, and we have tried to publish this code, which is for analyzing microstructures, and one part of that is a Hoshen-Koppelman algorithm. The paper is still under review, but the code is available for free to download from GitHub. I will share a link. It has got nothing to do with atomistic methods except for the implementation of Hoshen-Koppelman, which might be useful for some of you. Other than that, it is basically to analyze microstructures, okay, to especially anisotropic microstructures, irrespective of whether they are microstructures obtained from experiments or microstructures obtained from simulations. You can do the analysis. This is more like a statistical analysis of microstructures. So, we have this code. You can also extend this to 3D. As you can see, it is not very difficult. So, only the neighbors where you are going to look at, you are going to look in 3 directions instead of 2, and the same algorithm should work. Okay, so I already opened the code. So, let us run through the code once before we conclude. MIST. So, microstructure for what? Statistical? Yeah, microstructure statistics.
Means garbage.
Yeah, in English MIST only means the fog. So, okay, so hopefully no Germans. Anyway. So, this is a code that I have downloaded from this Tobin Fricke's web page, and it is in C, and I will also compile and show you how to run. The only modification I made is that this code had taken input from the screen. I mean, I do not know how he expected people to type all these things on screen. So, maybe it is for educational purposes. So I changed it. Now, I have made it to take inputs from a file and then do the analysis and come out of the analysis. Okay. So, the rest of the things are standard. So, this is standard inclusion of libraries and labels, right. You have to label the clusters, and this is the one which tells what he calls canonical is this. When we have 4 and 3, we said that the label should be 3. In Hoshen-Koppelman paper, there is a natural label and then this final label. This is the canonical label, and natural label is 2, 4 and 3, and the canonical label for all of them is 2. Okay. So, this part of the code basically does what I did here. Okay, 4 and 3 are there, let us call it 3. Go back and change all 4 to 3s, and go back and change all 3 to 2s, and so on. Okay. So, that is what this does. And this is a union. You can see it is a one line code, basically it is putting them all together, and there is the so this creates the new equivalence class. So, if you have a new point, it has to create a new equivalence class, that is what 2 is, and it will return that label. And this is initialization of data structure, and this is freeing the memory. Where was the find? There should have been a function called find. It is here. Okay. This canonical label has the find. So, it is basically an algorithm which consists of union and find. Okay. So, this algorithm is taught as an example of union find algorithm in this scheme of things. So, it is computer science algorithms course probably. Okay, so you print the matrix, that is the end, and this is the Horschen-Koppelmann, where you would return the total number of clusters found, and then this is the relabeling is only going to call and okay. So, this is checking the neighbors, okay, and this is the sample input and this is the output it gives, which we generated by going through the algorithm ourselves, and this is the main. So, this is the part of the code which I have commented out. I just replaced it by a file open and read the data, okay, and I generated a data file which had the same. So, if you can write from your sparks or lamps first the size of the array and then the spins at every site, for example, that is sufficient for this code to run Horschen-Koppelmann on it and tell you which are the how many clusters are there. Of course, this does not output the size of the cluster, but that should also be possible to do. So, you can check the code and add that part as an output, okay. And his output also gives where the clusters are by printing it in the same format, which is probably not something that you want. If you have a large this thing, you do not want to print it. Those things you can change, I mean it is not difficult. So, that is the code, okay. So, it is a very simple code and the idea is also simple, except for this keeping track, increasing this thing, and this is given, I mean whatever I have shown you is there in the Horschen-Koppelmann paper itself, and online you can find lots of implementations including our own implementation, okay. So, you can run, that is it, okay. It is very simple C code to do Horschen-Koppelmann. Okay. So, I am going to stop here. There are more scripts that I will post today. We did get from Kamalakshi the generalized stacking fault energy scripts that we use, not the one that I downloaded from online. So, that also I will share in the Google Drive directory, and I think we have not put our slides etc. yesterday and today.
I did.
You did, okay.
Except for this afternoon.
So, I still have not put, so I will put them also today. So, we are stopping slightly early today, maybe half an hour.
Maybe one short comment about this Horschen-Koppelmann algorithm, why it is so important. I mean, if you do it naively, you at least would spend, if you have n atoms or n points in your grid, n square attempts to calculate the cluster connectivity. And this is just proportional to n. So if you have very large systems, makes a huge system, huge difference. In my case, I have a million lattice sites, so whether it's n or n squared, it's 1 million versus I don't know, 1,000 billion or so.
Trillion, billion, 1,000 billion should become trillion, yes.
Trillion. Yeah, so it's an enormous difference. That's one point I wanted to make, and that's often very important if you have large systems, whether you make n or n square or something. Tomorrow I will also briefly mention Fourier transforms. Probably you know that this fast Fourier transform has a similar scaling behavior. If you do it naively, you have n square calculations to do in the fast Fourier transform, because it's why it's called fast. You have n log n calculations to do. So as soon as you have more than, I don't know, several thousand or so points, this plays quite a role. So at one point, and during this lecture I read a bit, this cluster counting is not only important for material science or population questions also, but it's also used apparently in image processing. And I guess you all know, if you process an image, for example, it can detect borders of regions or so. And this is also done, I think, using this Horschen-Koppelmann algorithm.
Yes.
So if you cut out something, all points with a common gray value or so, or transition from dark to bright or so. They just try to fit a cluster corresponding to this condition.
And percolation is also used in disease spreading.
Okay.
They are also percolation problems. You start from here, how far? You have people who are this thing, who can get affected, who don't get affected, but then you need a path to. So in virology and the areas also it is used. So I mean it has a much wider. Yeah. So.
I forgot for this percolation question. There is also a nice trick how to detect whether you approach this percolation threshold. And if you just randomly distribute particles on such a lattice, at some point the probability that you get a connected cluster through all the system becomes 1. This is called the percolation threshold. But this is only true for an infinite system. And of course, you can make your system larger and larger, then perhaps you at some point approach a infinite system. But I forgot the details. Somehow you take the second largest cluster and subject something, and then you get a nice divergence already for not too large systems when you approach this population limit.
I see. I didn't know about that. Yeah.
Yeah, I forgot. As I said, I tried it sometime in the 80s or so. It's 40 years ago. It's, something one can forget.
Okay, so I'm going to stop here. We will again meet tomorrow, but before we disperse, are there any questions or clarifications?